Hello everyone, welcome to MTech keynote this year. We're very happy to have Edoardo with us. Edoardo Tibuzzi is the design director in AKTII, has been involved in a lot of research, led practice there, teaching across the globe. He was with us in the morning session for our jury. Without any further ado, just want to welcome Edoardo here. Thank you.
So thanks a lot. Hi everyone. I'm a designer actually, and as Milad was saying, currently design director at AKTII. And first of all, I would like to thank Elif and Milad for inviting me today in joining your final jury, and to allow me to say a few words tonight. I guess there's an invisible thread that connects emergency to technology, and incidentally is a thread that connected a lot of, or I think the majority of the project that I had the fortune to be involved in delivering for the past 18 years that I've been working in practice. I enjoyed particularly this morning, I think, reviewing the students' work, and I'm sure that if you were there, you'll be able to recognize some or many of the challenges encountered during the course in the projects I will be showing you tonight. Where do we start? I think I just wanted to talk a little bit about engineering for a change. Engineers, we trained to solve problems, and so we do like solving them, but the harder the problem becomes, the more satisfying for us is it to solve. And incidentally, this is not a good thing sometimes. And this is not me saying it, it's actually Bill Baker from OMA. We've asked him to put some notes for one of our books. He was the principal engineer for the Burj Khalifa. And I thought it was quite interesting, his approach of saying like, no, almost like therapeutic self-understanding of his own practice, our practice. I think the postulate, this affirmation is just because we can engineer a solution, it doesn't mean that we must do it. And straight away you can perceive the gravitas, the responsibility that directly or indirectly is given to us when a project is starting. I think Bill's sort of intuition needs some expanding. And I think our work is about balancing the many different forces that are driving projects and their interrelationships, which is what you guys also are looking into in the course. So often materiality affects behavior. So when we're trying to master that with the tools that we've got, we find interesting relationships, but conversely, behavior also affects materiality, so it's not a linear relationship. And whilst it affects materiality, it does also affect geometry. So then the system starts to be more and more complex. And mastering that, specifically, especially in the early stages, can make it or break it in a project. But geometry also affects performance. And it's kind of like throughout the project delivery, that can take a lot of different turns. As you can see here, particularly in the vessel was interesting, where a particular distribution of the staircase meant that the kind of vibration and comfort performance was not quite easy to find in terms and control. And geometry also affects performance not only of the structure but also of the environmental impact. So while we're crafting our tools to understand and find this relationship, it's important that we do it in a way that we can use the information we retrieve to drive the design and not the other way around. But also, as we saw today, performance affects comfort as well. So, and I think this is an area where we're particularly interested. Oh, I don't know why you're skipping through, but as the intangible impact of the external environment has got a very big effect on what we are designing, and also how the building that we make are kind of see through and they develop and kind of expand into their design life. So our focus is always in the small, almost impossible target of integration of the various challenges we confront when we deliver a project, that very, very tiny bit in the middle. But how do we get there? And in our team, we sort of have a very strict and applied design and research approach. And for us, a lot of things starts with process. And kind of one of the way of seeing it is kind of going to the process of understanding and analysis. So going into the past and going to work out through the historical data of a particular project, and then formulate the hypotheses and the solutions. But also the other processes, the synthesis, the creation process. So looking at the future and what that particular project will have to comply with in the future, and also predict some solutions there. But in the process of analysis, we look at traditions. So often there's a perception that some solutions are more appropriate than others. But in every project, we must look at and carefully balance the conventional solutions with the non-conventional ones. That's where research comes through. And this is an important step to define the optimum outcome, whether it's when we look at the structural system or materiality, for example. And knowledge of a particular system is essential in highlighting methods of constructability, tolerances to work with, the expected movements, and also the environmental performance as a reference. So I think for us, when we start a project, it's always about looking at these parameters, but also looking at availability of a particular material or of a particular knowledge in the proximity of the site, because that drives sustainability and performance, but also drives cost. Location, of course, plays a big role in driving some of the choices. So this is a step that really needs to be taken into account from the very beginning, as this will impact our choices and how our interventions interfaces with the surroundings, but also how the installation methods are constrained, for example. But last but not least, also, I think culture comes into play, and culture really definitely shapes our building. This is what project we started with Fosters and Partners about 10 years ago. And it's just about finalizing and taking shape inside. I mean, let me just kind of sort of spend a couple of words on tools, because I think we all kind of are in the post almost digital era, and but tools are still quite relevant and important. And as I found, this picture quite interesting, the tools that are used to make a physical object, such an iPhone, they're not really necessarily straightforward. You wouldn't, if you see that picture in isolation, you wouldn't think that are the tools for an iPhone. But also, if you compare the tools that we are using in design, it's the same thing. The interrelationship between every single step and tools that we use are not kind of, straightforward. And when I joined AKTII in 2007, our team was already at the forefront of digital design. Already back then, we were experimenting with in-house developed tools that play with generative design. This was a bridge over Farringdon Road, where we're playing with occupancy and usability of the crossing, defining the geometry of the structure itself. We progressed that exercise and kept refining our weapons in that sense. This was again a software we did for delivering the Zaha Hadid's Heather Aliyev project, trying to rationalize the surface into the least amount of families of panels according to the fabricators' sort of molding capabilities back then, which weren't quite good as they are right now. And I think, again, this, if you look at with the eyes of today, is sort of straightforward, but back then was really trying to push the boundaries into how to control the process and how to somehow manipulate geometry and structure to make something that is efficient. And again, looking at the external environment and external boundaries for us always has been fundamental to understand what would be happening for our buildings, and how could we use that information, visualize that information, and use it to design better buildings. But obviously now it's different because the power of computation and possibility has exponentially increased, and it will do in the next 2 or 3 years or 2 or 3 months. So from one end, you've got the total freedom and total speed of making things, but also you're starting to somehow lose control. And I perceive that the challenge obviously is not any more aesthetic or geometric right now, but is focused on consumption reduction. So I think that finally computation can come in handy. So in kind of putting together some examples tonight, I thought to start with, I split the presentation in 4 parts, and I wanted to kind of start with the methodology. And with the project for us was quite fundamental back in 2016, where we had the opportunity of testing tolerance at the very, very high risk, at a hyper speed, and against all odds. And this was the Serpentine Pavilion with Bjarke Ingels in 2016. Why high risk? I think high risk is because this was, the Serpentine is obviously, as you know, quite constrained. And Bjarke Ingels wanted to use a material that was never been used at this scale. And the materialization of the pavilion was this idea as how a wall can become a pavilion if you unzip it. But when you had a new material and a new constraint and only 8 weeks of program, things can become quite tricky and almost impossible. So without a non-linear process that digitally connected the material to the geometry, to the performance, this project wouldn't have really happened. And at the time, constraints the competition were really, really tight. The pavilion was made out of sort of flat sheets of pultruded GFRP, which is a sort of a glass reinforced polymer, put together, glued together with the same material and interconnected by an aluminum connector. So the idea here was to control the materiality and the performance through the different distribution of the fibers in the different kind of slices of the material. That gave us a first opportunity of controlling structure. And as I said, the material was bespoke as well for its properties of transparency, of translucency, actually. It was very, very important for the architects to create this evanescent result at the end. So the fiber were very carefully placed around the different elements, which meant that we needed to kind of respond quite quickly to the different iterations, both in the macro scale, understanding how this wall performed against the external forces, but also how to kind of quickly communicate back to the team where the critical points were in terms of connections. So we kind of distributed, our methodology was to distribute on one end geometry and in the hidden layer understanding all those performances issues, but on the other end the output was the production element, so we could iterate quite quickly. And in doing that, we also started to highlight visually the features of the project to allow the architects to really visualize how the structure would perform aesthetically. And as an example, this is the box thickness mapping, which would allow them to understand the translucency in different areas. But for us, it was really interesting because obviously this material wasn't used before, and there's only so much you can simulate and digitally understand from something before some real-world data. So we had to kind of do our bit and digitally model the structure, but at the same time, building control was asking us to prove our results. So we had to partner with the university, had to make up a full-scale mock-up of a module, load it with the worst-case scenario, and then compare the result. And this particular exercise of comparing digital versus real was the actual exercise that convinced building control to sign off the structure. So as you can think, quite a critical moment in the, in the 7th or 6th week. And again, high risk and super high speed, as I was saying before. But it was not only that, the challenge. The challenge was obviously that methodology is also connecting the different actors in the project. So learning different ways of describing the same thing, learning different ways of talking about the same thing. But, and also controlling the final outcome, not only the manufacturing, but also how the things were coming together, as this step was fundamental to hit the deadline and to make sure that the pavilion could open in time. So all, in the end, it worked out, but I think it was largely due to the kind of thorough and rigorous way of setting up a methodology that didn't only work for us, but worked for the wider design team. This is a couple of shots, and I think from here, from the video, you can appreciate in some kind of angles the translucency, which is quite beautiful. So I think methodology is where I would start, and then moving on to alchemy. I think topology and shape are the intersection of architecture and engineering. So, as I said, the challenge has changed. It's not only anymore about aesthetic, it's also about challenges in climate, and this is us starting to perceive from our clients. There are stricter and stricter sort of embodied carbon limits that we need to reach, and often those are almost translating into status quos, and material on its own cannot really carry an intrinsic value. Often we hear and referring to timber as being good environmentally, but it's difficult to do that measure, especially when you are measuring the impact of a material against climate targets. Of course, if we're just pointing the finger based on what we've been done so far, the contribution is clear. But also we have to be careful because we are just at the beginning of the journey of understanding things. So equally, all that glitters is not gold. So we try to do a bit of an example above. As an industry, we are trying to learn of the impact of the increasing demand, for example, for engineered timber. So it's imperative that we use this resource wisely. As you can see, when we learn about forestry and how long would it take to grow a specific amount of engineered timber for a specific project, the scale starts to really put some question now. So it really needs to be the right reason to use the right material as opposed to just checking one choice. So I think I just tried to put a couple of examples on this. And the first one is the LSE Marshall building with Grafton Architects. This has been a very interesting project for us, has been designed to be in line with the RIBA 2030 carbon targets with a 150-year lifespan. And I think time is important in the whole discourse here. So the structure is made of concrete as the most appropriate material to deliver the required architecture functionality with a low operational energy in the long term. And I think what I found interesting about the scheme is that obviously the brief from the client often drives the choices. So in this case, the scheme was looking at providing a sports hall within the basement, a great hall throughout the ground level, and a variety of academic and study spaces at the top with multiple level of offices. So you're starting from a very large space at the bottom and going to a very tiny room at the top, which is not what you would do, logically, but this is what the project required for the specifications. So there was tons of engineering challenges here, from the delicate context outside to the tricky transfer due to the program requirements. So I think for me it's very important that we're looking at a solution, topology and shape really drives the solution and the efficiency. So the intuition here was to resolve the space distribution to utilizing a rotating grid, which had two twists of 45 degrees. And this kind of operation posed a column spacing of 15.2 meters at the ground, then at 10.8 meters in the study spaces, and back to 7.6 for the office spaces at the top. So with this kind of very, first principle intuition, we resolved all the transfers of the structure, avoiding structure gymnastic, avoiding spending material where it was not needed. So we really used topology to drive the shape, resulting in an efficient engineering solution. And then incidentally, obviously, the concrete also became exposed to kind of revealing these beautiful perspectives around the building with the trees that now define the building architectural identity. So for me, this was a really kind of interesting example on how by driving the geometry and the shape, you can find efficiencies. The second project is that I thought carried interesting lessons is the Google campus in California. We worked at the very early stages with Big and Hedwig Studio to develop first the master plan for the client, and then some of the buildings. And here the ambition was to create a Buckminster Fuller kind of type of envelope, and to free up the internal buildings from the facade requirements. So to develop an office that could be truly adaptable and would not really have to stick to the constraints of the facade internally. This was actually their Big and Hedwig first collaboration. So the challenge structurally was to find a lighter, a simpler, a more flexible and adaptable system that would comply with the high seismic and wind forces of the bay. And in the early stages of the concept, we looked together with the architects to create a form-active structure, investigating the efficiency of creating stiffness through curvature. And that kind of form finding allowed us to introduce cable nets, which are lightweight tensile structure, and that rely on the high pre-stress forces at the perimeter to generate stiffness. So on one end, we could create a reduction in material expenditure, but not kind of affecting the reliability of the structure. Then moving forward, we also developed the design looking at an hybrid system, which eventually became the final solution, which is kind of a combination between a traditional grid shell and a cable net. So this is quite lightweight and economic because it's sort of singly curved. So it's simply and quick to fabricate, and it's constructed by layering of steel bars into rigid networks. So I think this project for me was quite revealing in a sense that covering such a large span, it would have not been quite straightforward, but also in a way we've utilized the structure for many other reasons. So the canopies in this sense are covered in solar panels, which supply 40% of each building's energy. And they are also found to collect water into storage tanks down in the basement, which makes the building water net positive. And in California, this is a big thing, as the country or the region is always suffering by a long period of droughts. So again, topology here and shape, once again, are being manipulated to create architecture and engineering, which is performative. And then the last examples in terms of sort of alchemy, I would say, is the Red Sea development. And in this case, with Foster's and Partners, we looked at developing the entrance to the resort. And I think I found this project interesting because the condition in which we were operating, so the location, had a lot of different challenges. So the site ecology was driving the whole design, trying to minimize the contamination of the water. We weren't allowed to use concrete or minimizing the use of concrete as much as possible. We're also looking at regional resources and availability of timber there. Obviously, the local climate had a massive impact, and the intention of the architecture to create this barefoot experience. So for us, again, the response was also looking at prefabrication. A modular approach as to deliver the pieces down was a challenge on its own. So in this sense, choosing timber made an awful lot of sense, and choosing a topology that allowed us to manipulate the surface to create lightweight grid nets, again, made much more sense. So we developed the schemes following a similar methodology that I showed you earlier in the pavilion, but with a higher degree of understanding of the timber behavior to kind of, again, further rationalize and minimize the amount of material. And timber is quite interesting as a material because it's pretty much a plastic behavior. So there's a direct relationship between the curvature and the stresses. So you can't bend the material more than it can take, as it would break abruptly with difference from concrete and steel. So in this case, we've really been playing with these relationships and also playing with the detailing of these relationships to kind of create the final shape from the initial architectural intuition. And again, tools allow us to do that quite quickly nowadays. But it's not about the process of form finding most of the time. It's about how the verification of the final result can be taken in place. And again, this allowed us to really explore more relationships, to create different typologies of structure, and the system allows really to then plot out and go into fabrication a lot quicker than it used to be, as you know. But again, the project is on site at the moment, and it was quite interesting to see it growing quite quickly through the process. I think then the challenge that we have doesn't get resolved only by manipulating topology and structure, doesn't get resolved about optimizing. It does need an extra look. And I think in the series of projects I'm about to show you, it's kind of the contextualization of the challenges about how we make sure that we're adapting some building stock to extend the life and to capture carbon. And that's the final bit of the recipe that I think we all should start to really question and look at when we start a project. And I'm going to start with 100 Liverpool Street, so it's just down the road. And this is a project with Hopkins Architects. And in here, the brief from the client, from British Land, was quite simple. Just take two tired 1980s buildings and transform them into the gateway to the new Broadgate campus. It could have been easy to just take the buildings, demolish them, and start afresh, except that the constraints below made it quite difficult. We had to keep the station operational. So we really need to, we sort of did a lot of work into looking into a menu of extending the building stock life to make it into a new life. And we have identified a series of operations that can be implemented. And in this particular project, I think we hit them all. We reclad, we add a portion of the building, we took away other portions, we went down, adding some basement, we went higher, adding some stories, we reused all of the foundation, and we infilled. So again, it was very interesting how the project developed. So this is kind of where we started. The challenge was to extend 40% of the additional floor area without strengthening the foundation. And how will we be able to do that? So it started with the real challenge here was really understanding what was on site by poring over thousands of drawings and archive images. So it was literally a forensic engineering approach that helped us determine the potential of the structure. And then through computation and through analysis, we sort of justified the intuition. So we took the existing frame, removed what we couldn't retain, we kept as much as possible, including all the foundation, and then we extended the frame only where needed. But that meant that we also needed to use quite important sort of approaches to understand how to maintain and extend the existing frame, so where we kept the existing loading paths and strengthen only the column that requires strengthening. And again, without the tools that we have at the moment, this is a very complicated exercises. So this methodology will be even more powerful when the data of the building will be accessible digitally in form of building assets. And for this reason, we started to develop compute in-house that will allow us to drive this agenda, so storing all the digital information about a project, so then in 20 or 30 years' time, where we're going to have to reoperate on it, it will be a lot easier. We're not going to have to do that forensic exercise that we had to do for this project. So I think that obviously, in all, this building, it's incidentally British Land first net zero building, so it's been a monumental effort from all the design team. But it really also is a first test case that showed the potential of keeping the building stock as much as possible, using also computation to enhance that. And another example that looked at instead going higher is the South Bank Tower. In the original developer-led competition, we team up with CIT, which is the client, and KPF to look at these sites. And we won on the basis that we were the only team proposing to retain the existing tower rather than demolishing it. So I think this, again, shows the perseverance and the confidence, in a sense, that we need to have at that point. But at the time, we confidently suggested to extend the tower by 4 stories. But the more we understood of the existing scheme, the more we been able to be more confident. And in the end, we ended up extending 11 stories. And partly was because of the use proposed. So we were converting from an existing office building into a residential, which meant that comparing existing versus proposed loadings and changing the final usage, we were able to assess a lot of spare capacity in the frame. But again, when reusing an existing structure, it's important to have a good understanding of the resilience of the existing building and the impact that the additional loads have on the structure to limit and reduce the use of new materials, keeping the carbon balance. So a lot of the exercise here was to assessing the spare capacity and then play with the little, with different materials and different materialities up until we would reach the original capacity of the columns. And the ambition was not to kind of modify or strengthen again any of the existing. So it was really a process of looking at the past and looking at, again, at the existing information, which was quite scarce, but also looking at the future. And in this project, I think we've been able to use, for one of the first time, computational fluid dynamics to understand the actual wind loadings on the tower. And I think this was a key step in demonstrating that the original design was very conservative. With this analysis, we've been able to reduce the wind loadings by 40%, that meant that the existing tower, and in particular the core, had plenty of spare capacity. And we used this argument to extend additional 11 stories. So the existing core has been extended, and cantilevering was sprung out from the supporting lever to kind of pick up the stability of the last bit. But I think it's a monumental, again, example to seeing how we need to rely a lot more on the existing building stock and rely a lot more on our capabilities to kind of create new spaces. So I think in reflecting these things, I think research has got a very important role in kind of bringing all those lessons down to the paper. And we've been quite firm throughout the 25 years in looking at research as a method, as a mean. And the project I'm about to show, I think, are looking at materializing intuition through research, often with little to no budget. We see a lot of examples in the academia, especially, that are looking into important steps in research. But when we are practicing, often research is very difficult to fund. And I think we are being quite good in being able to pick and choose the project that really explore different methodologies, different materialities, pushing the boundaries of material, let's say. One of the projects I really enjoyed the most is this with Zaha Hadid Architects in Roatan. And the reason is because it kind of had some sort of a holistic approach on how to create a new modular system through the specification of the architecture with a component-based design, with a platform that allows the clients to start from their occupancy levels, so a box defining where they wanted to be on site, and then delve down deep with the configurator into the interior design. So it was a completely controlled approach. And for us, that meant that in the background of the system, we had to define a structural approach that kind of matched all the different potential configuration. And we had to kind of played it back into the platform to allow those choices to materialize. So that was the first step, trying to kind of define a method that works with the choices of the client. The second constraint was to try to define a typology that would work. So really creating this kit of parts that could be reconfigured around the different choices of the client and allow the different permutations of the structures to, again, being able to choose from the catalog of structural system and kind of apply it to the configurator to make sure that the choices of the client were, in fact, possible in the end. But zooming out, I think the most interesting part of this project was to really relook and rethink about local timber supply chain. So we went down there and we identified two main producers from local certified forests in mainland Honduras. We looked at how they processed raw materials, and we created a proposal for a new factory that would take that material, process it in, and by using digital construction, would create these modules with a lot more tolerance and a lot more control. So the project went through, and it's currently on site, and the Circular Factory took over the definition of the system. And I found interesting that that approach translated into, again, a platform that now can control the fabrication of the pieces and how they come together, which means that we have a lot more control on waste, a lot more control on timeline and the execution of the project. And again, through digital control, we can schedule every single component of the system and understand the implication of timeline, again, cost and manufacture. So I think it was an extremely interesting opportunity to really look at the full scale process from design to creation to manufacturing and to installation. And again, it's a way of actually looking at the potential of the tools that we can now implement. The second project I'm showing in terms of research is a project we just did in Venice. And I'm just making a big jump from tools to materiality. So this is a pure material research. We don't do that often. I think the previous one we did was the Serpentine Pavilion. But it's been a very interesting collaboration with urban radicals, as we really wanted to, again, define a methodology of looking at a potential reuse of waste material, creating a new building component material using waste, use it, and potentially then reuse it in the future application. The premise was this. In Venice, canal dredging waste gets collected every 6 months, with small sort of boats, and it gets deposited onto an artificial island outside the main city, which is called Tresse. This kind of like, it's an interesting thing, is a completely untapped material. It's highly toxic when it gets collected, but it gets purified, or it gets cleaned up before they deposit it. So the idea is, what if we use this to make a new brick for Venice? And again, the whole research that we initiated was to define more the methodology rather than the output. We had to kind of make it into something in the end, so the whole architecture was inspired by Venetian heritage, and it was designed with the location in mind. We've installed it in the Giardini. But the whole idea of having the interdisciplinary team of architects, engineers, and manufacturer was really to define the process. And in the process, the first step was to identify the containers of all the different ingredients for the brick, and trying to define this radius to where to source the material as close as possible to the site. So we did do the exercise. We identified all the places where to collect crushed concrete, crushed brick and mortar, the stone from the pavement of Venice. There's quite a lot of waste that goes into that, which is perfect to be part of the component of the brick. Glass and ceramics from Murano was also looked into, as there's a lot of waste from the chandelier manufacturing there. But most importantly, how to use the main component material, the waste mud. So we did embark on the exercise. We went down on the island. We had to get special permission from the Italian Ministry of Transport to extract this mud, apparently. And they thought they were crazy, but we tested the process over here, mixing up different aggregates and different kind of mixtures, including using natural tensile fibers such as hemp or sheep kind of sort of mantle to create some tensile properties. And then we tested the process. So we specified a very strict results in terms of compressive tensile strength requirements. We did the testing over in the UK and in Venice to make sure that the final bricks were compliant with the regulations. And these are completely unfired, so it's a very kind of super low carbon approach. Those are some of the test equipment and the test specimens that we used to kind of perform the tests, which were returning quite a high concentration of stresses and strength. Because of the availability of the material, we had to kind of split the number of bricks, so we couldn't use all of the lime. We had to kind of make a regular lime brick with the sort of without the mud, but we also had half of the installation was made with the Tresse silt. And of course, we used computational methods kind of drive the geometry. And we collaborated with a highly skilled manufacturer down in Venice to put all the ingredients together, following our recipe, which was the most difficult part, just to make sure that they were sticking to the concentrations of different aggregates and to test the quality of the system. So the process was highly controlled. The brick is only pressed, so by carefully manipulating the strength of the pressure, we made it possible to create strong bricks. This is one of the initial samples made down in Venice. So the whole process was quite a a challenge, as again, time here was of an essence. We didn't really have much time. Here is where we installed the pavilion, and this is a little bit of a process on site to follow our geometric patterning to show the actual different manipulations of the installation. So I think it was really interesting, and we ended up actually reusing a previous pavilion, the 2021 Cyprus pavilion, to make also some internal furniture, which then the pavilion became almost like an open air library where people could come in, leave a book and read a book. And in the whole exercise, we managed to sort of make a very interesting material, roughly a third of embodied carbon that is content of a regular fire brick. And it was so successful that the Design Museum actually asked us to give some samples to be part of the How to Build a Low Carbon Home exhibition. So I think, for me, this kind of almost summarize all the challenges that I've been showing in the previous projects, how to control shape and geometry, how to control materiality, and how to make it in a way that we can also reuse the building stock or waste in our environment. But there's one last thing. I think I did talk about external environment and how that can make a big impact of what we do as designers. And I think this project is really interesting for me because it summarizes how we cannot really look at a building in isolation and really need to kind of understand the intangible effects that that building is obviously applied to. And planners and regulators are making a big effort in forcing us to do that. But intuitions often are creating interesting results. So this project was an attempt of creating a waterless garden in the desert for the Sharjah Triennale. And we really tested our capabilities and understanding of our tools on how to perceive and control the geometry of those gardens to make sure that we could create vegetation without water, but just by manipulating the local microclimate of the system. So really, it was about designing with data. And this project, we were lucky enough to be selected to be part of a 3-year program of research where we made the thing and we had 3 years of time to test and assess the data to test the validity. So the idea was really to kind of pick up from where in Lanzarote they left it off, this idea of confronting the adverse climatic condition and creating vineyards where it was really not possible. In Lanzarote, the inhabitants of this volcanic area have created this kind of ingenious wine growing system where they made it possible to kind of overcome the lack of rainfall in 300 years. So the vineyards grow in funnels, which are surrounded by little walls that are protecting the vines from the very high temperature winds. And also the funnel overnight creates condensation that also enhances the microclimate. So this is what we actually use as an inspiration. And we use, again, our tools to be able to define the depth of those and the diameter of those larger funnels to grow vegetation. So we did several tests, and we looked at, obviously, the overall cumulative results. And we went and built the thing. And we also installed sensors. I think we installed a control point sensors on the roof to understand the variation, and then we installed 3 sensors across the different gardens. This allowed us to live visualize the real data on the spot for visitors to explain what we were trying to do. But also now that we are at the end of the exercise, allowed us to really relook at all the data that we managed to extract from the sensors, which span from temperature, soil moisture, the solar energy, the leaf wetness, the humidity at the ground level, and really kind of trying to start to understand the kind of output that we've been able to put together. And I think it was been quite successful because we really started to really understand the overlaps between the different properties. And as you can see, the vegetation kept constantly growing without the addition of water, as those kind of pictures are showing. This is when we installed and the first plants. This is a year after, in 2021, where you start to see the vegetation growing. And the interesting bit was that cooking section selected the shapes, the typologies of vegetation present in the wider region to provide a menu in the bar of the school. So the vegetation would also grow some fruits and kind of would all be edible. And this created the menu in the bar, which was quite nice. And this is kind of the final result. So I think it was really, for me, really interesting to see that kind of opportunity in real life and how we can extend that into larger developments. And then I want to sort of, I'd like to conclude tonight with a video that we produced for, again, Venice Biennale in 2021. And this was for an installation made by Daniel Lopez and Jesse Reiser and Nagano Umemoto, which kind of meant to kind of give messages about architecture. And there were a series of videos reflecting on climate, actually, the climate challenge. There was Kazuyo Seijima, Timothy Morton, and it was quite nice to be included in that and being able to say our version. So we put this video together by reading some data available on the internet, and I'm just going to let it play, and I hope you liked it.
As the human race is determined to reduce emissions, to prevent the catastrophic effects of climate change, this is not a process that can be entered into blindly. Wind speeds are constantly changing and increasing. Earth works under the laws of equilibrium. And different forces are affecting each other within the globe container. We can now visualize those interactions. To help reflect on the causes and potential mitigations. At AKTII, we have visualized NOAA satellite data captured over a 20-year period to look into the pattern of CO2 emissions around our globe. In the search of equilibrium, we need a paradigm shift.
Yeah, so I think that was really interesting for me, that zooming out and being able to kind of manipulate and use the data that is available, that satellite actually information, really gives you the perception that what we're really trying to do here now, it doesn't quite make a massive change if we're not really looking at the right scale. But it's important that through research and through academia and through collaboration, we keep pushing the boundaries and we keep researching into methods that allows us to deliver better buildings. So I hope you enjoyed tonight. I really want to thank you again for the opportunity and for coming tonight, you that are here and people that are online. And thank you.
Thank you, Edoardo, for this great lecture. Now we have time for questions. If anyone from audience has any questions.
Hi there. Vicky from TP Bennett. I was interested in your proposals for reuse, extending the tower in London. Are you finding that you're having to do that retention study more frequently? And how are you finding that agenda shifting in the work that you're doing?
Yeah, no, that's a very good question. Thank you. I think for us, we've always looked at how to retain structure because it's one of the best way, of course, to hitting budgets and to comply with extending the life of a building is our priority. And I think regulations are coming in hands to that. Obviously, the targets that we all been asked to kind of hit are becoming stricter and stricter to a point that for some particular buildings or for some particular clients is becoming almost the only way to be able to afford and to pass planning, especially again in the UK where these things are starting to be a lot more regulated, which I think I found it quite refreshing. The important is not to be too constrained about it and to hinder creativity and obviously the final output. But for us, it's not only about retaining a specific structure, but also how to perhaps engage with the concept of future adaptability of the system. So making sure that the choices that we're making right now are also compatible with potential different uses in 30 or 40 years' time to avoid that building gets demolished. So I think that's what I think space syntax and again, control of the choices right now, it's important to make almost like a building survive. And I guess, I mean, the Grafton building, for example, was an interesting thing because that design life also plays a big part into it. So by deciding that building needs to stay there for 150 years, it is quite bold, but it's also quite refreshing because by then it allows us to really have to make this thought process and make sure that we make a structure that is flexible enough to extend that life. Otherwise, it won't work, and the law of commercial law will take over. So I think it's really interesting.
I'd like to ask you a question about. I'd like to ask you a question about timber. Yes. Since there are so many thousands of different types of timber, when you're designing, how much account do you take into the specific properties of one species against another?
It's again a very, very interesting question. As there's timber and timber, so there's engineered timber, which usually kind of really funnels down the opportunities in terms of species. But there's also, in some occasions, you can use typologies of timber that are more kind of varied. But I think when we, in the application of timber that we've been able to deploy, we've been using a specific engineered typology. And I think the interesting part of that is that it's more or less the diagram I was showing you before, is that by concentrating the choice on a specific species, because that is the species that becomes the certified timber product, then we are altering the ecosystem of a forest, because then we suddenly have to plant more of that species, and we kind of don't give space to the other ones. So the whole ecosystem of the forest gets challenged. And interestingly enough, a lot of the carbon is not stored in the timber itself, but is stored below ground. So altering that ecosystem, we're starting to look that it's becoming a problem as well. So yeah, I think, again, looking at the challenge a lot more in depth, and as we learn the issue, we are more, not concerned, but more attempt in making that choice of the material, so we use it only when it's the only right choice to do, let's say.
And do you try and express the specific species? I remember Renzo Piano did a beautiful pavilion for Olivetti, using bamboo with aluminium connections, and it was, I think it was in the 1960s. But what was so exciting about that was the bamboo was, expressed as in its own right, which was good.
Oh, no, absolutely. Bamboo is a fantastic, incredible material, and we actually did an installation at the Royal Academy last year with Marina Tabassum in bamboo with aluminum connectors, actually, incidentally. But I think it's an interesting material because it can be eaten, it can be used for making paper, it can be processed to make bicycles and products, underwears, socks, down to houses. The challenge with bamboo is obviously its own durability in specific areas. In Bali, for example, is perfect because the conditions of the environment it tends to kind of extend the durability of the material itself. But there are also opportunities of actually maybe laminating and making it into a product, which is actually something that we're really interested in, and starting to put some research propositions for that. Because again, it grows a lot faster than timber. It's got a lot more capability of retaining carbon. So it really does sound as a better answer to a certain extent, but I'm sure there's also other pitfalls that we're not looking yet. But definitely an amazing material.
And the last question, what about insects? Because I understand that, building in the Caribbean, for example, using timber is a real problem because of the timber being eaten by insects.
Termites. We did this very nice canopy down in Gabon, in Libreville, Central Africa, and again made out of timber, and that was one of the major challenges in terms of making sure that the first 1.5 meters of the supports were protected against termite attacks. But there are ways of actually protecting it using repellents or just thin films to protect the timber itself. And again, timber is quite a versatile material, but also it offers a lot more. It's a live material, it's an orthotropic material, so it offers a lot more challenges in terms of humidity control, in terms of fire and charring, termites attack. So it really needs to, again, be looked into more thoroughly than other materials.
Thank you.
Hello, thank you very much for your presentation. I know you mentioned adaptability in the middle of your presentation with the Google project, and I wondered if you could expand on that a little bit. In particular, how you engineer a building for resilience in the future in terms of loading conditions or use cases which you may not be aware of in the onset of a project, and how that influences how you approach the design process, as well as how do you do like checkups afterwards, or how do you consider the use cases after?
Thanks a lot. That's a really good question. I think we could do a complete separate lecture about adaptability, and I think it's really important because also we are it's difficult to predict what's going to happen in 100 years, but I think in terms of structure, the Google example you mentioned was a really interesting approach from the architectural team, because creating an envelope containing buildings that wouldn't require an envelope was an interesting take on how then the internal space can be flexed and can be kind of adapted. So in this system, we allowed for extra capacity in the columns to extend the height or contract and extend the height. We allowed for larger sort of opportunity of loading at the base to perhaps moving some buildings, or again, future-proofing and extending the building itself. The stability system is completely decoupled because you don't have the impact of the wind on the internal building. We could actually largely remove the cores and use just the moment frames for the structures to, again, reduce the constraints of a core element. But obviously, that needs to be looked at into complying with fire regulations and circulation. But again, these were the things that we looked at. Incidentally, in Google London, which we are still now on site with the same team, we also looked at manipulating floor plates. So the structural system in that project allows for suspension of lightweight timber slabs. They are suspended from the main structure at the top, which would allow the client, again, to expand and contract the floor plate to allow for future flexibility in terms of growth or reduction of staff, let's say. So there are also other different ways of looking at flexibility and adaptability. But I think for structure, those are the primary ones. And again, I think that the South Bank Tower project shows you then it's difficult to predict what happens, but largely things are getting lighter and lighter. So ideally, especially if we manage to move into performance-based design and step out from the codified approach that we have right now, we will have a lot spare capacity in the future in our building. So that would allow us on its own to, again, extend the life of them. So it's just about proving to the authorities that that's a safe thing. That's why it's going to take a bit more time, I think.
Great, thank you very much.
Okay, if there's no more question, I'd like to thank you, Edoardo, again for this great lecture and your feedback in the morning. Thank you, everyone who joined online and here lecture hall, and have a great rest of the evening.
Thank you.